Recording. Perfect. Okay. Okay, let's get started. Welcome, everyone. Feel free to, again, unmute, use your camera, use the chat if you're not, if you don't want to do that. So it'll be good to know how many people are real people versus bots, not that bots are not real people. It'll also be good to know where people are from and what what you're looking for. Yeah, I think a bot would say not a bot, right? If you have good training data, you should say not a bot. But it'll be good to know a little bit as we're going along what, how many people are here sort of students, how many people are in industry, how many people are in academia, just so that we can start tailoring some of the things that we're talking about for the next few hours. Um, the um, quick quick uh, overview of what we're going to be doing. So this is going to be kind of interleaving. We're going to be going through talking about some of these bias and fairness issues, but then also going back and forth from breakout groups back into the common. So we'll do about four breakouts throughout the next few hours. That's going to be more interactive and hands-on. Yeah, so I think let's get started. Just to make sure people know some of these links, all the content, there are links to Jupyter notebooks, Python notebooks, and the content and the slides and everything, so you can access that. Just make sure that all of that is working. So if you go to the first website, that's with a link in the Zoom chat, that gets you everything that you need to have for today. You don't have to install anything to run the notebooks. We're using Colab, so it's just a hosted. As long as you have a browser and unfortunately a Gmail account is required, you should be good. Um, and yeah, so here's kind of the plan for today. We're gonna go do quick intros for all of us, but um, we basically want to start by talking about overall fairness and equity at an overall systems level and outcomes level, as opposed to just the machine learning model level, because the machine learning model is useful, but not the only piece in a system that it's built in. We'll then go to a breakout exercise where we'll talk through case studies and um, explore sort of sources of bias in different case studies. Then we'll come back together and talk through fairness metrics, and then we'll go into again breakout, where we'll take the case studies we covered and think about how do we go from what we want the goal of the system, the social societal goal to be, to the fairness metrics. And then we'll take a break to kind of recover a little bit. Um, and then we'll switch to the coding hands-on part. So the first piece will be an intro to how do we audit our models for bias and fairness. Then we'll go into the breakout and use the Jupyter notebooks to audit a bunch of models that we've built for different types of biases. We'll then come back and talk about different ways of reducing bias in these models, and then again go into the breakout group and try a few different types of strategies that people have proposed to reduce the bias. And there we'll try a strategy and then we'll audit it again to see the before and after. What did it change? We'll come back and report back from this reduction work, what worked, what didn't work, and then wrap up with sort of some highlights and checklists to kind of think about. So it's about 3 hours, so it's long, but it's a lot of content here. So we'll move quickly. We're not going to go. The idea is not to give you a depth first view. It's going to be a breadth first, where we're going to go over a lot of content. In the slides, you're going to see many slides that have a sort of a star at the top. That's content that we think is useful, but we don't have time to go into. So instead of kind of just sort of hiding them, we just thought we'd make it available so that you can look at it afterwards. There are a lot of references and papers and details of what we're talking about, but we're going to try to be fairly high level in the concepts, and then the code is where we'll go deeper and hands-on. Yeah, so Pedro, do you want to start by doing introductions and move to Kit and and me?
Yeah, sure. Hi, everyone. My name is Pedro Salero. I'm a PhD in machine learning. So I'm coming from the computer science background until I fortunately started to work with Raid, and it kind of opened my mind to real world issues of bias and fairness and how AI is really impacting our society. So I was postdoc with Raid at this app at U Chicago, and now I'm working at the industry at FitZai. It's a fraud prevention AI company in where I lead the AI ethics research group. So doing work on fairness, explainability, accountability, and so on.
Okay, great. Kit?
Yeah, I'm Kit Rudolph. I'm a research scientist at CMU working with RAID as well on a lot of these issues and kind of projects spanning the machine learning and public policy kind of intersection. My background's actually more in the natural sciences and then in public policy, and spent some time working on campaigns and in government and things like that before kind of coming back to academia.
Okay, and yeah, so my name is Raid Ghani. I am faculty member at Carnegie Mellon in machine learning and public policy. And the context for, so the idea behind this tutorial is really where we've been coming from for the last many years. We've been working on all the buzzwords: machine learning, data science, AI, with different government agencies and nonprofits to help them build systems that are designed to then help the people they're trying to serve. Right. So the idea is, how do we better build systems for providing public health services, providing educational programs, employment programs, social service programs, and what sort of really the work we started was less starting from bias and fairness, more from, we want to build these systems that have the outcomes that we care about. And what sort of, over the last 7-ish years, we've worked with, hundreds of government agencies and nonprofits across the world in health, education, criminal justice, social services, economic development, disaster relief, public safety. And there's lots of these, so the link at the bottom has a list of these projects. But the idea was that when we started working on these projects, the goal of the projects was really to help the people these organizations are trying to serve. And one of the challenges we saw was that a lot of the organizations started with the premise of, we want to be more efficient. We want to make the best use of the resources that we have, the most efficient use of the resources. And often what that meant was that the primary objective became efficiency, and often efficiency would then make it more expensive to help everyone who needs the help. Right? So in all of these cases, in a lot of the projects that we work on, we have limited resources. We want to help this many people. We only have resources to help this many people. And the question is, how do we select the smaller number of people? And if we just pick the people who are easiest to help, that means we can help more people. We leave behind people that are much harder to help, and that leads to inequities. So we started kind of thinking about, how do we build these systems that can have equity, fairness as a primary goal, and balance that with efficiency and effectiveness in a way that's much more analytical and embedded into the entire process of building these systems. And in this tutorial, we're really focusing on the bias and equity and fairness issues. There are many other issues around ethics in these types of projects that are critical, that we need to think about when doing these types of projects, around privacy, data ownership, transparency, accountability, all those things. We're focusing on the bias piece here, but keep those other things in mind. There are lots of good resources for that. So we're not going to cover them here. I think the big sort of high level concept we're kind of going with, saying the systems that we're building have to reflect what we care about. So if we want a society that is fair and equitable, then we have to embed it into the system. We have to design the systems to achieve that. And it's easy to sort of say that, but I think, the question that as people who are building machine learning and data science systems, we have to sort of think about here's kind of the guiding question for us when we're working on projects, which is how do we develop the system that can help us make decisions that lead to fair and equitable outcomes? And the reason sort of it's phrased this way is fair and equitable. So there are two pieces here that are sort of important, right? One is help make decisions. And it's help make decisions because most of kind of critical high stakes decisions that are being made are not automated decisions. There's a human somewhere in the middle that used to make that decision by himself or herself, and now is being guided or helped by a computer. So how do we make sure that the help results in more equitable and fair outcomes? The second piece is the outcomes, right? So a lot of the work you're going to see in machine learning, fair ML, and sort of fairness in machine learning and AI and data science is going to focus on making machine learning models fair. And that's a big distinction. You can have perfectly fair models resulting in horrible, unfair outcomes because of this human in the middle. If you have a perfect model that's fair and the human reverses every recommendation that's being made by the computer, then the model was useless at getting fairness. Or you can have a perfectly unfair model, but the human is really fair and they fix all the recommendations and do the right thing, right? And so the idea is, how do we design this combination of the model, the system, and the human combined together, applied to society, leading to fair and equitable outcomes? The question is, what do we mean by fair and equitable? What are the outcomes we're thinking about? And so what we sort of want to do in this tutorial is start with that framing, start with thinking about overall fairness and equity, not just the model fairness and equity, but overall systems level, which is everything embedded, right? So if you're trying to use the system to figure out how to do outreach to get people vaccinated, and which is going to be a problem, over the next couple of years. One day, eventually, there'll be some vaccine, and then we're going to have to figure out how do we prioritize those. And if we're using machine learning to figure out who most needs help, that model could be fair. But then let's say you start doing outreach, and the outreach program is only in English. Well, that's going to be unfair and not going to reach people who can't speak English. And so you have a perfect model resulting in action that's not fair, resulting in outcomes that are unfair, and vice versa, right? So step one is going to be, sorry for the beeping, it's the chat in the back for the conference. So that kind of step one is thinking about overall bias and fairness. The second piece is going to be thinking about, if you've been exploring fairness in machine learning, you've seen lots and lots and lots of papers on metrics. There are a bunch of metrics. There is, precision parity and recall parity and false emission rate and false discovery rate and false negative rate and false positive rate and true positive rate and all sorts of them. And it ends up being confusing. It ends up not being confusing, even to us who understand these metrics, but people who are consumers of these systems, business owners, policymakers. It's very hard to figure out what metrics do I use. And so what we're going to do is kind of give you a framework we call the fairness tree, which starts from what are your social goals? What are you trying to achieve as outcomes? To what are your fairness goals? So what is the problem you're trying to solve? What are the interventions you're going to take? And then use that to figure out what metrics do we care about. So that's going to be part two. And part three is going to be, once we've figured out what are the metrics we care about, sorry, this is really annoying. I'm going to just turn that off. Once we've figured out what metrics we care about, we're going to go and do some audits. So we're going to take a bunch of models that we've built, and we're going to learn how to audit them for different types of biases. And then we'll go into a few different types of bias reduction strategies and explore the impact of those reduction strategies on the bias of these models. So that's kind of the overall agenda for the day. Yeah, so that's kind of the high level agenda. we'll just go into part one, which is thinking about overall fairness when building these types of systems. And so again, this is going to be kind of the recurring theme for the day. Our goal is not to make our machine learning model fair, because who cares? A machine learning model is just a way for us to get to some decisions, to then get to outcomes. And so the overall goal is going to be making the system fair and the outcomes fair. Not the model fair, not the predictions fair. That's kind of, those are useful. We don't want to ignore those things, but eventually we care about the overall system, which is the model, the pipeline, the person in the middle, and then the overall outcomes. And so here's a typical process, right? We have some model that we've built. We use it to recommend some actions. Let's say the action might be this, one of the case studies we're going to cover is going to be, in banking, for example, you have a model that's being used to decide if somebody should get a loan or not. And so the model does is estimate the risk of not payment, of this person is not going to repay. It's not saying deny a loan or give a loan. It's just saying, here's the risk this person will not repay the loan. And so the loan officer or the bank or some entity in the middle is then deciding, should I give them a loan based on that risk or not? And that action results in some outcome for this person who does or does not get a loan. And so the overall goal is for us, not to just make the model fair, but make sure that the outcomes for this person are fair. The thing to keep in mind is that we want to make sure that we compare when we do that to something, not something perfect, because no system is going to be perfect. But compare it to what's being done today. So today we are making a lot of the same decisions, maybe without using machine learning, maybe just with a human, maybe with some rules. And so the question becomes, when we build these systems and figure out that they are biased, well, do they need to be perfect, or can it be better than the status quo and still improve outcomes for people more than the current system is doing? And that's going to be sort of, and it's the same idea as any other evaluation metric, right? If you're trying to improve something, you want to have a baseline that's the current system. The baseline is not 100%, and if the system you've built is not 100% correct, it can't be used. And same goes for bias. I think it's a question of sort of societal question of thinking about, if we have a biased system, is it better to use that than an even more biased system? Or we should wait until it's perfect before we can start using it. The piece to sort of think about a little bit deeper is, when we're looking at bias in our systems, there are many sources. The most common thing you're going to find when you're looking through this is people will focus on the data. Well, the data is biased, and that's why models are biased. Well, yes, data is probably biased. Every data is biased in some way or another. But the sources of bias, there are many more sources, right? So the biggest source is really that, unfortunately, the world is biased, right? The way people interact with other people is biased. The world is racist. The world is sexist. And that world is what causes a lot of the data to be biased and everything, the entire outcomes to be biased. And so I think that's the biggest source we have to kind of look at, is there is bias in the world. That bias sometimes instantiates itself in the data, but then data, the way we choose data sources, that's biased. The kind of data we use, that's biased. The way the data is collected, there are biases in there. Then our analysis pipeline, the machine learning pipeline we build, and we're going to go a little bit deeper into that, that has a lot of biases built in because of the way we choose to do certain analyses. And that's our fault. That's not the world's fault. That's our fault as people who are building these systems. Then sometimes there's a human afterwards who can and is in many cases biased. So even though you get this human review, there are cases where the algorithm makes a prediction, the human sort of says, nah, I don't believe you, and ignores that prediction or overrides that prediction. So there's biases coming from there. Then the actions that are taken. So in the case of the banking finance example, giving a loan or not giving a loan is the action. The pipeline is giving an output of risk of not paying back the loan. The action can be, oh, I know these types of people and they don't pay back. So even though the computer said low risk, I'm not gonna give them a loan, right? So you might introduce bias in there because of the human. No, feel free to keep asking questions in the middle. We'll pause and answer them as they come along. So feel free to put questions in the chat as we're going. So the way to think about these project when you're starting is go through each of these steps and see what kinds of biases are going to be introduced as you're building a system or you're solving the problem, right? So here's an example. In the data sources side, bias might come from what data sources you choose to use. Is it data source that contains, is there going to be sample bias? So you can have rows missing about people because they don't appear, they exist, but they don't appear in this data set. Are you going to have cells about, so let's say you're doing a survey or you have a data set from a survey and it's missing information, or so you ask pregnant women if, how often do they smoke? And there's most likely going to be some error in that answer. And that's going to be not equal for every person. So there's going to be measurement bias, which is how you answer, how you got that each cell. There are going to be sample rows that are going to be missing. And then if you're predicting outcomes of some sort, let's say you're predicting who paid back a loan, well, there's going to be error in that label because you might have not collected certain data. You might have a hard time linking things. So thinking about what are the different sources for bias in the data. And there's sort of more details here, right? So sample bias is a really common problem, especially when we use data that's not comprehensive. If you're using, let's say, social media data, it's not going to have coverage across everyone. If we're using data that's, again, credit scores, for example, they're going to be more accurate for people who have a credit history. Let's say you're, a non-US citizen, you just moved to the US and you're going to have no credit score. Doesn't mean you're not credit worthy, right? But that's a bias in the data source that you're using. And so there's lots of these things that are worth, and we'll go into that a little bit more in the breakout. Labels is another one, right? We sort of often assume in a lot of machine learning work that when we're building these models, we have perfect labels because why not, right? And it turns out labels are also noisy. So for example, if we're working so one of the projects we've been working on for a few years has been with police departments on predicting which police officers are going to do horrible things, shoot people, use unjustified force. And the label for that is, every time a police officer uses force or has an injury or causes an injury or there's any sort of weapons used, a report gets filed and then internal affairs department of a police department decides, there's an investigation and decides justified, unjustified. And that's the label. It's, will they have an unjustified use of force? Now, if the internal affairs department is totally corrupt, they say, well, everything is justified. So they never label anything as zero, or they rarely label anything as one, or as unjustified. Now, if you give a model that data, doesn't matter how good your model is, there's no way it's going to be able to correct for that noise, that error. And that means it's going to generally predict not, perfectly justified because that's what the training data is. So we can't really, the model can't be fair if this labels are totally unfair because you're not going to be able to easily correct for that. So it's sort of important to understand whether that could be a bias in your data where the labels are bad and what other proxies could you get? What other types of sources could you augment that can help you deal with that? The entire machine learning pipeline, bias comes in a bunch of places. It comes in through data. It comes in through record linkage. When you're linking different data sources together, we sometimes mislink two people who are not the same, or we miss the links because these two people are the same and we don't connect them together. And that is sometimes based on their spelling of their name, because people with long names with lots of consonants tend to get misspelled and then they get mislinked, or people with similar names Common names tend to get linked together incorrectly. And yeah, so somebody's saying, any kind of data collected through sensors, it comes with its own errors, that depending on, how accurate, how reliable, how widespread the sensors are. Data processing. So the one big thing that happens a lot is, we do things like missing value imputation. And most people don't think too much about that. It's like, well, we'll just, either if you're a stats person, you just drop a bunch of them, bunch of rows and bunch of columns. If you're, default, you just do sort of mean imputation, which is a horrible idea, because let's say 80% of your data is males and 20% is females. If you have, let's say, a variable that's missing for a female, if you take the mean of that variable, it's going to be dominated by the value for males. So now implicitly, you've now made this female look much more like male to the model, because you were just taking mean imputation. And so you have to kind of think about, what kinds of analysis you're doing now, what are the decisions you're making at each step, and how those decisions lead to downstream bias in the model, in the predictions, and in the outcomes. And each step here, you have to kind of go through and think very carefully. And then this piece of sort of when you intervene on people, when you act on these types of predictions, you override some of the predictions. Like in the loan case, you might decide, I don't believe this computer because I know better. And that could introduce bias. Or if the prediction is to do outreach to vaccinations, but you're using, just let's say you're calling people on phones. Well, then you can only reach people who are answering their phones. And so the post modeling, you still have a bunch of places where you could result in, things could result in bias. So what we want to do next is, we're going to break people into three groups. We have 3 different case studies, and Pedro, Kit, and I will split up into the 3 breakout rooms. So we'll randomly assign people into 3 breakout rooms. And if you go to the website, there are, we're going to have breakout rooms 1, 2, and 3. So if you go to the website, you're going to see here. Let me go and share. You should be here. So we're going to have these 3 case studies. We're going to have the loan denial decisions, social media to assess damage and responding to natural disasters, and after school programs. So we're going to have 3 breakout rooms, and each breakout room will pick one of these to go through the case study and try to answer some of these questions around sources of bias. So let me, we're going to go, so, okay, I'm creating breakout rooms. I'm going to create 3 rooms. And let's see, assign participants into 3. It's going to assign about 25 people into each group randomly. And breakout room 2 and 3. And then you guys will be in one of these rooms. And we'll stay there for about, I think our plan is to be there about 15 minutes and go through the case studies and come back together after 15 minutes. So, okay.
And are we presenting once we have finished that exercise, or what's the sort of the?
We're gonna do, so I think for this.
Okay, so that's good. Yep. The KED organizing.
Yep.
Okay.
Yeah, so Kit, do you want to do recap of some of the session, this your session, and then we can move on to the next?
Yeah, so in our session, we were talking about a case study where a school district is trying to identify students at risk of not graduating on time to offer additional support, like tutoring, after school programs, things like that. I think we really discussed a lot more detail the first and second questions, kind of ran out of time to talk in lots of detail about the third. But there are lots of sources of bias in the underlying data, different reasons why students might fail to graduate, some which might be more measurable than others that may split across populations. Certainly observation problems. If students are moving across schools, across districts, you might not measure the labels for those students, whether they graduate or not. You know, different populations participating in different types of programs, either school-based or outside of school, that might also either be, you know, easier or harder to measure. In terms of the machine learning pipeline, talked a bit about kind of record linkage problems, especially with non-Western names, Unicode characters and things like that that often run into trouble, as well as talking a lot about kind of the assumptions that people bring when they do feature engineering, and they kind of have this causal graph in mind that might not be wholly represented, or there might be things like mental health issues that aren't as well captured in administrative data and can't be measured and can't be implemented in the models as well. And then we talked a little bit about how those different reasons why students might not graduate on time might impact the effectiveness of different types of programs. If students are leaving school because they have responsibilities to their family, offering them additional tutoring might not, isn't solving the problem that's actually there. And so, you know, that kind of captures the, quickly the pipeline that we talked about. Oh, yeah, thanks for sharing that. Yeah, Pedro or Ray, do you want to give a quick readout of yours?
Pedro, you want to do a quick?
Yeah, we just started writing down. People were writing down different sources of bias. We are somehow privileged because that was your running example throughout the sources of biases. But people mostly mention the risk of people from specific groups that are not well represented in the past can create some sort of sample biases if we use the historical data from the previous bank decisions. Also, the previous bank decisions, if we use that data, we not consider how was the past the economic growth of the applicants after they got the loan, because they actually are not on the sample. And there is a risk of once we deny the loan in the past, we actually don't know if this person would actually be able to pay or not. So we have that sort of reject inference there. In terms of linkage, and also talking about the use of credit risk scoring, the example you mentioned on people and new immigrants coming to US, there is if we have features about credit risk, they will be just zeros because there is no data about these people. There is also a risk that also based on our target metrics of increasing the likelihood of getting repayments, it will for sure be biased towards people with wealthier applicants that will be able to repay that in the past. And in terms of downstream fairness risks is really the risk about perpetuating these prejudice cycles of access to financial services.
Sounds, yeah, I think those, I mean, I had an easy breakout because it was mostly focused on the issues with social media data of disaster. You know, there's a lot of projects we see, especially at KDD, there's a lot of papers that have happened over the last few years on using social media to do disaster relief assessment. And you know, a lot of the people in the session in the breakout room talked about sample bias, people who don't use social media, whether it's older people or don't have internet access or use other platforms other than Facebook and Twitter. If they're using Snap, if you're or TikTok, right? At least for now. And then kind of a little bit more nuanced around data that might be missing geocoding, which might be, desktop laptops by default versus mobile phones, and or people who are more likely to post things, and completeness of the data and the reliability. Is it actually true? Or if the geodata is wrong, versus an analysis, how would we figure out ground truth and quantify these types of things? And then what types of neighborhoods would we over allocate resources to, versus who would we under allocate resources to based on these biases, and gaming and things like that. So that was kind of a quick overview of the sources. So now that we have an idea of where, again, the idea, we're trying to go through things quickly so you have a feel for what steps to take. In a real project, this would happen over multiple sessions with different types of people involved. You would have the team that's working on the project. You would have people who understand the domain and the data and the community that's going to be impacted, and understand who posts on these types of things, what kind of things they post about. So it involves lots of different types of people, and this would happen over a period of weeks or months rather than 15 minutes. So the 15-minute was just to give you an idea of what kinds of questions to think about. But this is a topic that takes quite a bit of time to go through. And so now that we've kind of covered this, we're going to switch to going from, how do we think about, from sources to getting to what are the metrics that we care about. So Kit, do you want to take over from here? And I'm happy to switch slides.
Yeah. Do you want to present, I guess, in that case, or I can?
Sure. I can.
Sure.
Yep.
Cool. Yeah. So, now that we've talked a little bit about kind of this, idea of overall system fairness and how it breaks down into different components, the next piece that we wanted to chat a little bit about briefly, and then we'll go and do a kind of another breakout conversation, just like this last one, using the same 3 case studies, but thinking about the particular metrics that we might want to measure in these different cases. And, if you've kind of read the literature, there are a lot of different metrics, that exist, kind of on, anything you could imagine. And I think, it's easy to get confused and a little bit lost. One in, there are 20 different metrics. There are 6 different names for each of the 20 different metrics. So there are 120 different things to kind of juggle. I find it confusing, and then people who don't work in this area, who are like actually making policy and thinking about these things and maybe reading about them in the news, find it confusing. So let's see, right, if you click the next slide, and this is just to kind of like make this point a little bit more, directly, that you need a way to sort through that kind of zoo of different things. And so you kind of want to start from like, what are the social goals? What do we actually care about in this project, in this problem? And how do those map to our concepts of fairness in that context? And then how does that concept of fairness map to a machine learning metric? And kind of following that path down, we find is a lot more helpful in understanding this. And I think this is something even in some of the projects we worked on where kind of our thinking evolves a lot as we go through it and start with, kind of like, oh, here's the metric, here's the way we kind of think about it. And then we take that and present it to policymakers and they say, oh, that's not how I think about that at all. And so this is also, I think, Wright's point about the 15-minute, breakout session is really kind of a distillation of this would happen over months and lots of iteration over the course of the project. So the same is very much true here, and often it's not even just one single thing that you care about. So let's see if you click to the next slide. So this is just kind of making that point again, right? Demographic parity, impact parity, FDR or precision or false emission rate, false positive rate. Right, there's, this endless list of things. If you can go to the next slide, and all of these kind of map to the idea of or many of these map to the idea of the confusion matrix. And any of these colorful boxes on this image famously stolen from Wikipedia can map to some concept of fairness or something that you might want to equate across groups. And often you're saying, well, what's the right denominator and what's the right numerator, right? Who do we care about equalizing certain types of errors or certain types of opportunity or predictiveness across. So if we jump to the next slide there. And I think another result that probably, is very familiar to most folks here is, that all of these are kind of tightly coupled together to each other in relationships between these different rates and the underlying prevalence. And so there are incompatibilities, right? If you move one up, others might be forced to go down. So if you click through here, so this is, one illustration from, a couple years ago of one such incompatibility, and there are, many others that you'll see. So for instance, if we were thinking about the false positive rate, the false discovery rate, and the false negative rate, right, we can write down an equation that maps these things together with the prevalence. And if you look at two different groups with different underlying prevalences, so if it's, male and female students might have very different rates of not completing school. Well, if this, if this first term is equal and, or if this first term is unequal, the prevalence is unequal, and we wanted to equalize the, false positive rate, and, if we wanted to care about two of these, right, if we want to equalize the false positive rate and the false negative rate at the same time, but the prevalences are unequal, then that would force the false discovery rates to be unequal as well, right? Because you need something to balance out the inequality and the prevalences to make this equation hold. So I think that's, a well-known result, and people have shown different incompatibility theorems across different sets of metrics. This one's just a easy one to kind of illustrate. There's a fair bit of literature on this, and I think, right, one kind of wrong conclusion of that is to say, oh, well, you can't get fairness, right? That like you can't make your models fair on all the things at the same time. So maybe we should just shrug it off and not worry about it. Maybe that's a little bit of a straw man, but I mean,
it's a realistic straw man, because at least I have heard this from people in different companies and governments saying, oh, we read these papers that say that we cannot have fairness, and so should we just give up on having fairness if we want to use machine learning? And the inverse of that was saying, well, if we want fairness, do we use machine learning at all? Because it looks like machine learning can't give us fairness. And so that's that implication, implication of misunderstanding that, could be people say, well, we shouldn't use any of these tools because they're inherently unfair. And the point is that, if that's true, then we should all stop and go to some other session about real estate and finance instead of fairness and bias. And if it's not true, then we should figure out, what do we do about it?
Well, and I think, I mean, right, the two kind of branches of that, the sort of straw man-ish, like, oh, we just don't bother with fairness at all. Let's just push ahead and not even measure it or care about it. But the other that I think, you raised, that's a good point, right, is, or people say, yeah, we shouldn't use machine learning. But, the confusion matrix, right, like that, the confusion matrix is not a tool, exclusively of machine learning, right? The human decisions, a judge's decision or a a caseworker who's deciding who, you know, who gets additional assistance and who doesn't, right, those decisions also map to false positives, true positives. And I think that often gets lost as well, of, you know, that these impossibility theorems don't just hold for machine learning assisted decision making, they also hold for any decision making that's mapping individuals to, you know, some sort of binary classification. So I think both of those things are worth kind of discussing, and especially worth kind of keeping in mind as you talk about these things with stakeholders and policymakers and people who, you know, either might say, well, we want it to be, you know, fair on everything, or if, you know, you say it can't be fair on everything, then we're not going to, you know, bother. But yeah, so we can go on to, so just to kind of, you know, put some concrete context around some of these, you know, specific metrics and what they would mean, or how you would kind of, you know, describe them to somebody who's a little bit less technical. We'll go through kind of, you know, one example that sort of kicked off a lot of this, which is a model looking at kind of bail determinations. So that's, you know, keeping people in jail pre-trial. If you click through, I think we, yeah, I guess we don't really have. So I imagine most people who are in this session would be familiar with the Compass case study, which is this, what, 2015, 2016, something like that. Journalists or journalism outlet called ProPublica got a hold of some data from a model called Compass that was being used in kind of judicial decisions about making bail determinations, and did kind of a bias audit and looked at some of the error metrics there, and found very big disparities between Black and white individuals, and you know, and wrote a piece that you should, you know, if you haven't read, you should go out and read. And you know, and this kicked off a lot of research because then oh yeah, thanks. Somebody just posted the piece in the chat. The company that made the model kind of responded and said, oh, but if you look at, you know, precision and false discovery rate, you know, there aren't any biases. And then they did a follow-up sort of saying, you know, how confusing they found it, that the model could be both biased and unbiased at the same time. And, you know, and so it really kind of put out there this argument about whose bias definition is right in a given context, you know, which ones can hold concurrently, and all that. So I'm sure this is, you know, review for most folks here, but because it's gotten a lot of, you know, I think everybody mentions it as their kind of motivating example. But if you haven't seen it, yeah, definitely go read about it. We'll just kind of, you know, walk through, yeah, sort of this concept of the fairness tree. If you go back in the slides that Ray just jumped through, and you'll see there are kind of a bunch of like pieces that talk through, you know, what each different metric might mean in that particular context. And so that's something, if you look at the slides after, you can kind of walk through as well. I think, you know, something that has helped us think about a lot of these problems in projects that we work on is kind of organizing our thoughts this way into, you know, this tool that we call the fairness tree, where we really look at, you know, helping guide kind of the conversation with policymakers and stakeholders about how do we think about bias and fairness in this particular context. And so, you know, the first kind of big question we ask is like, well, is your is the thing that you're doing more punitive, like the Bell determinations or maybe inspections of properties or things like that, or is it more supportive? So is it helping students with resources to graduate, or support for paying your rent or food or things like that? So if it's punitive, we probably care more about, kind of areas of inclusion, right? We care more about doing harm to people who we predict as high risk, who we intervene on, that shouldn't have been intervened on, like keeping an innocent person in jail. If it's assistive, we may care more about areas of exclusion, about leaving people out who really do have need. And then, kind of following down the tree, you really kind of start to ask, well, what's the denominator? Is it among, everyone in this group, like all men versus all women? Is it among people who should be intervened on? That is, people with need, or people for whom the punitive intervention is kind of correct? Or is it among people that, the model predicts one way or the other? So somebody asked, oh, and great, just answer. So somebody was asking in the chat, the algorithm itself is discriminatory. So, right, and this kind of comes back to the ideas of, overall system fairness, and whether your resources are limited or not. And then somebody else was asking in the chat, what if we don't have the features related to gender, race, sometimes the case in industry applications and things like that? And I think this is actually a really good point, and something that we run into sometimes as well, where people say, oh, well, we don't, want to collect that, or we don't want to, give you that because, or, the kind of common thought like, oh, we don't want to include gender in the model because that will make it biased. But if you don't measure it, right, you can't measure the biases, you can't do anything about the biases, right? In some cases, maybe there are proxies you can find, or imputations, or things like that. But, I think the kind of fairness through unawareness concept has really, proven problematic. And so I think sometimes the answer is, well, you should go out and collect that data for the purposes of making things more fair. I don't know, Ryan, Pedro, if you have other thoughts on that, but it's definitely an important point.
I was just typing in. Yeah, I mean, I think there are two. Sometimes you have it and you're not allowed to use it, and sometimes you don't collect it because there was no reason to before. And I think both of those are, if you want the system you're building to be fair, whether you care about it as an organization or whether you're regulated, there is no way around it. You're going to have to spend the money in collecting that data if you don't collect it, and you're going to have to convince the organization to let you use it, because otherwise there's no way to magically figure out. You can have proxies for it, but I think this is the business case you have to make to say we need to use this information.
And additionally, it's kind of almost serves as an excuse to kind of living on this an awareness of not being able to know what is going on if you actually don't collect that data.
Right, yeah, and the other point about proxies, of course, is, right, if you are using proxies, then all this, name to gender lookup tables, well, there may be biases in, maybe that lookup table was generated just with Western names or things like that. So, I think, yeah, I think, right, when you start using proxies, then you start kind of having additional layers of potential issues. Yeah, and somebody mentioning, right, lacking all the relevant covariates, which I mean, and of course, right, with any kind of machine learning problem, you certainly always lack, I guess, unless you're doing physics, you lack all the relevant covariates. And so, yeah, a lot of this work, right, is trying to put, either fairness constraints or optimizing for those things kind of jointly as well as performance. So I don't know, right, if you want to jump to the next slide. So this is a tool, it's out online.
We are on the fairness tree, right?
Yeah, do you want to jump to, yep.
Did we talk through that?
Yeah, I think so.
So,
talk through kind of the branches. Was there something more you want to?
Yeah, I mean, I wonder. So we are at 10. We're at 1:15, right? So I'm trying to see, is it worth kind of taking an example that from the case studies and kind of walking through that example here? Because I'm not sure if we go through that, or we can give up the break and go and skip the break. Because I think it's worth taking an example maybe. And right, right. So if we look at or even the compass example here.
Well, I mean, so yeah, why don't we take the school, we could take the school example here and give up the breakout. So, if, again, right, in this example, if we have a school district that's trying to intervene on students who might, not graduate on time, and they're, offering kind of additional tutoring or after school programming, that would put us on the kind of right side of the tree here, right? This is an assistive program. It's, focused on helping those students. Actually, Ray, do you have like a highlighter or
yep,
something?
That's what I'm doing now.
Okay, oh, perfect. Nice. So, that feels reasonably straightforward. And let's kind of think about both of these branches first. So let's, first say, well, about 10% of students don't graduate on time, and they have resources to help the, 10% of students overall. So we're not really facing a very heavy resource constraint. So then we would, say, well, we can help most of the people or most of the people with need. So we kind of go down the right side here. And then, that would kind of lead us to say, well, so we're in this case, we're going to care about different metrics of exclusion, right? What students that have need are we leaving out? But there are different ways to think about that. And each of these different ways kind of relates to the denominator, or you could put these in probabilistic terms, right? So let's, just for example, take kind of men versus women, male and female students, right? If we just said, well, what about, the rate at which we miss students just by virtue of their sex, right? So the number of false negatives that we miss, but among men, or the fraction of false negatives divided by the total number of male students divided by versus the fraction or the number of false negatives among female students divided by the total number of female students, right? So that'd be like the probability of being a false negative, being missed when you do have need, conditioned on just your sex. So, that might be kind of some sort of global idea of fairness, but one limitation of that idea is that the prevalence may be very different by gender, and in fact, at least in many of the programs that we've worked with seems, to be the case that that the completion rates are very different by sex. So then you might start thinking about, well, what about instead the, oh, I see you're just TPR for this. So, okay, what if we wanted instead to focus on the students with actual need and say, are we helping the same proportion of students, or are we missing, equal proportions of students who actually have need? Then we might focus on the false negative rate, right, which is the number of false negatives divided by the total number of label ones, right? So the total number of students with need is the denominator. The number of those students with need that we miss is the numerator. And, that feels like one reasonable way to measure fairness. One challenge that you might encounter with false negative rate parity in like a real world deployment in actual application is the fact that if you're just intervening on the students kind of above your model threshold, the students that you do intervene with, you don't know what you have kind of a counterfactual problem. You don't know what their outcome would have been in the absence of the program. And so you don't actually, it's hard to measure the denominator for false negative rate parity because the ones that you do intervene with, you don't know necessarily what would have happened to them otherwise. And so, one other thing that you might think about is, well, what about all the people that the model doesn't choose? So the people who don't receive, the students who don't receive this additional tutoring or after school assistance. What if we put that, use that as our denominator and then looked at the rates of, essentially the rates of not graduating on time among those groups. And so that would relate to false emission rate parity. In some ways, this might be something that's easier to measure, or you might see kind of measured in like a press article, right? Among the students who aren't helped with this program, the rates of graduating are very, very different by, gender or race or something. So each, and there's not really a right answer here. Each of these might be reasonable kind of depending on your concepts of fairness, how you think about your goals, how the policymakers, how the stakeholders think about these goals. And so, often this is both the conversation between all those people and even something where sometimes you want to look at the trade-offs across these in practice in your models and how well you can kind of do with different ones at the same time. And then, we'll spend just kind of a minute or two on, but what if we don't have resources to help most people? What sort of challenges does that impose, and why do we kind of have that called out separately in this sort of decision tree here? And, there are kind of some pragmatic reasons for that. So for instance, if I can only help a very small fraction of the individuals with need, the false emission rates, I'm, not going to be able to really move the needle very well on that, right? The denominator is going to look a lot like, right, the whole population minus epsilon, and the numerator is going to kind of be, the population of people with need minus, some kind of relatively small epsilon. So the false emission rates are going to actually look a whole lot like the overall prevalences, and be very hard to equate. The false negative rates are going to look very close to 1 because you're going to be missing most of the people with need as it is, unfortunately, because you have very few resources for your program. And so in that case, we often think about the true positive rate, which is just 1 minus the false negative rate. So, it's still kind of a reflection of the false negative rate. So recall or true positive rate as a way to to think about equalizing some sense of fairness there. And this really maps to what you might see in the literature called equality of opportunity. So this is, if you read like Maurice Hart's work, kind of the metric that he's thinking about there, which is sort of saying, well, if I look at the population, you know, of male students with need and female students with need, what, you know, am I kind of, at least, I can't help everyone in those populations, but am I at least, you know, kind of providing an equal opportunity of help to the different populations, right? Am I, you know, kind of helping people with need from, you know, male versus female students at equal rates. And so that's how we kind of land on recall true positive right there. So that's kind of a quick walkthrough of some of the ways that we might, you know, think about this. And, you know, again, just like the other breakout, right? This would be a you know, kind of long conversation and thinking a lot about balancing different things. And, you know, and is also a little bit stylized in the sense that, you know, we're saying, well, you know, this program is purely assistive or this program is purely punitive. In, you know, many cases, inspections is a really good case where if you're doing health inspections, you might say, or even like child welfare inspections, you know, you might say, well, from the perspective, if we're doing health inspections of restaurants, from the perspective of the restaurants, right, it's kind of punitive. Oh, you're hassling, you know, the restaurant and going out and looking for you know, issues that they have or finding them. But from the perspective of the clients of those restaurants, the people who eat there, right, you're protecting them. It's assistive. You're protecting them from getting, you know, sick or food poisoning or whatever. And so you might imagine that, you know, in many cases, it's not, you know, clearly down one avenue or down the other. You might be thinking about balancing different things or looking at different things. And really we're trying to, you know, provide the, this as kind of a discussion, you know, tool, so that this isn't meant as prescriptive or like, here's the answer. And, you know, you just follow this and great, I've got my one metric and go run with it. It's a little bit more of a decision, you know, discussion aid to help kind of structure the conversation and think.
And again, I mean, to Kit's point, you know, this is not, if you're a person building a system, these are not our calls to make in some ways for the system developers or the machine learning people. This is, as Kit's saying, a tool that we use to have discussions with the people who are designing the goals and the policies, and so it's really a way for them, you know, we in a machine learning system, and we're gonna sort of need the bottom layer, right? What metrics do I use? But asking your users what metrics should I use is going to be a pointless exercise, which many of us have probably tried. And so really, this is a way to sort of, okay, if your interventions are punitive, then you care about, you know, false positives are much worse. And so disparities there. And then depending on who you care about, and if your interventions are assistive, so it's really giving them a way to go from what do you care about to what the parameters we want. And we can, you know, AUC is a really good one. I think thresholding at 0.5 and then calculating F1 is the best way to do this. And for those of you who can't hear the sarcasm, please never, ever, ever, never use 0.5 as a threshold for anything in life, because pretty much nothing is 50-50. So yeah, so I think this is, keep that in, you know, and some people ask for references. I put in a paper that uses this fairness tree that we've developed for a specific project with Los Angeles, and then that reference is also in the slides. But yeah, so very, you know, this is kind of a 5-second or 15 second, right? In the school case, we would go in assistive and we would sort of want to help and we would pick these things. In the Compass case, where the intervention is punitive, right? We're keeping them in jail. The question is, you know, which of these do we pick? And people, and it may be that we look at, if we want to make sure that we have false discovery rate as equal across groups, then we would pick sort of this parity. But that's sort of the process we want to think through before, because we can audit for whatever metric we want. If the metric is not right, the audit is kind of, it'll tell you it's fair, but it's not the right metric, right? So
in that case, right, the false discovery rate is kind of a concept of like the gel population, right? So, are there equal rates of, if the gel, people in gel are kind of looking at each other and say, well, you've got this many innocent people, in gel from different groups, right? You're thinking about that as your denominator. Whereas the false positive rate is looking at, well, what about everyone who, is innocent or here, like, wouldn't be a flight risk or commit another crime or whatever. So, a lot of these come down to like, what's the relevant population, what's the denominator, and how do we kind of conceptualize that? And those two branches are exactly what the ProPublica false positive rate versus false discovery rate, what that argument between kind of ProPublica and North Point, I think, the Compass. People.
I think that's a good point, right? Is if you go back and look at that discussion that happened on Compass, right, ProPublica said the system is unfair. North Point came back and said, no, it's fair. And they were looking at these two branches, and it was fair for one metric, but not fair on the other metric. And I think the bigger issue there was that when the system was developed, the requirements didn't say, make sure the system is fair for this attribute. It was just make sure you build the system. And the developers arbitrarily chose a metric, developed it, released it, deployed it, and it wasn't done explicitly. And that's kind of what caused a lot of the issues. And so I think that's kind of one of the things we're pushing for is before you build a system, figure out what you're trying to do with it. Then develop it to achieve that goal. That doesn't guarantee that the goal is right and the goal is good. You could still do horrible things, but at least so you're starting with a more explicit goal. Okay, so I'm gonna clear out the circles, and we kind of talked about this piece already. Okay, so we're going to skip through some of these things around legal, and there's a lot of work going on in the legal space right now around how do you bridge this gap between the different algorithms being used and what are the precedents and other legal tools. So we're going to skip through that. So now we'll switch to, we have an idea about what metrics we're looking to audit for. So how do we audit the bias and fairness of our system? So Pedro's going to take us through that piece.
Yeah, just a question about the break. I think it was scheduled a break right now. Yep,
it was.
do we want to give like a 5-minute go get a drink of water?
Yeah, we can. Let's through
the time.
We can do people want to? You don't. The polls are disabled, so we can't really ask people.
We can't do that.
Which is very fair. We can't ask anyone, but maybe we can be unfair to the people who cannot type, and the rest of the people can tell us very quickly.
Yeah.
If you want to break
reactions.
Yeah, you can do
thumbs up or whatever. So maybe a thumbs up if you'd like a quick couple-minute stretch your legs.
Maybe the answering the questions is the break.
There's a couple in the chat. Yeah, a couple minutes, 3 to 5 minutes.
Okay. Okay.
And then we're back. So we'll kind of shift gears. It'll be a little bit more hands-on coding. We'll be using Colab. So you may also want to go click on that link during the break if you have a second. But it should actually be pretty quick. We've been banging on it a bit. Cool. Yeah, so why don't we reconvene
40 minutes. Yeah, whatever time zone you're in, 40 minutes after the hour.
Yeah.
Unless you're in India where there's a half an hour difference. Okay, sorry. Yeah, so somebody was asking about, can we talk about the bank case study and the fairness tree? That's an interesting.
Edra, one quick thing before, sorry, and then yeah, let's do. But the I guess the next breakout, we don't necessarily need to do the breakout rooms. We could do that all together for the hands-on bit, I think, right? Because if we're missing people in the...
Yeah, that's what I'm worried about is
the one after is a little bit harder to do.
So right now, if I go into the breakout menu, I see if I go in, let's see. This is such a bad interface.
On the screen share, it just looks like you're...
I know. I'm just clicking on white.
Yeah.
Oh, come on. This is really... Okay, so breakout rooms. And if I delete all the rooms, I'm going to delete all the rooms to see if I can start from scratch. 79 people still, but I think 79 might be the ones that are left now.
No, there's 112.
112, yeah. Yeah, so I think it's only letting me do breakouts for 79. So I think we'll just stick to...
But yeah, if we want to run through the bank.
Yeah.
Sorry.
Yeah, so bank is interesting one, right? Because we can sort of think about the bank as, in our case study, the bank was, they want to use the score to deny a loan based on the risk. And so in that case, if we assume that that means that the intervention is punitive, which means that denying a loan is going to be bad for people, which is, and so now the question becomes, because you could reverse it, and the other way would be, you're going to use the loan to decide who needs help and give them a loan, and then it's a system. So this is the punitive case because it's a bank. You know, they don't help people necessarily, right? They want to, because if you go back again to the case study, the goal was to increase repayment rates for the bank. That's the business goal for the bank. And for whatever reason, for now, let's assume that for regulatory reasons, they have to be fair. And so then, which group are we most concerned about, you know, that we're fair? Like, so FDR would mean people that we denied the loan. Are we wrong about, so basically we estimated a risk of repayment or risk of not repaying the loan. And so a false discovery rate is predicting a 1 when it shouldn't have been a 1, when it should have been a 0. So we predicted, we decided not to give this person a loan, but our estimate was wrong, and they would have repaid the loan. So do we want, for all the people who didn't get loans, who were denied loans, do we want equal rate for across, let's say we care about race, across multiple races. So that's going to be the FDR parity. But if we care about, you know, all the people who they, you know, the false positive rate, do we want that to be equal, versus just the false positives, the number of people we got wrong divided by the group size, right? So it depends on what the overall goal is. If we say that we want to be fair to all the people we deny loans to, or we want to be fair across racial groups when we deny a loan, for people who we are wrong about, then we're going to want to do FDR parity. But you know, Kit Feather, is there a case for FPR parity here?
Well, it's even it can become even more complicated because we might not know the true label if we don't give the loan, right? So FDR is probably a good metric to go.
Right. But, and I think that's, you know, there were a couple of questions in the chat, right, about the labels. If we don't, and that happens in pretty much every project, you know, every problem is, in this case, if we didn't give a loan to somebody in the past, then it's very difficult for us to know whether they would have paid the loan back or not. We don't have a counterfactual of people paying back loans they did not get. So if you decided you will never give a loan to a person living in a specific zip code, then there's no way for you to know whether you're being, whether they actually needed, you know, whether they would have repaid the loan or not. So if that's going to be one challenge, and there are a couple of papers that kind of dealing with that, but there isn't a really good way of dealing with that without doing some experimental work, whether trying to do some randomization and testing things. So that's a good point. But in some ways, I mean, the way I think about it is, what is at the end of this process when you're giving loans to people? Denying loans incorrectly is hurting people. Giving loans to people who didn't need them is an opportunity cost. At the end, it's what is the world that we're living in, right? So if everybody got to, just like the jail or the prison example, is if everybody who was denied loans got together, but they actually would have paid them back, but the system was wrong about them, what does that mean, right? So that society then becomes a place where we have lots of people who are capable of giving back loans. They need money, but one group is disproportionately not getting it, which means that group is economically suffering where they don't deserve to. And another group is getting the money. So I think it's that question of thinking about the outcomes. What is the implication of, if we get FDR parity, what is the implication on the society, versus if we have FPR parity, what is the difference in the two outcomes for people? Okay, Edward, do you want to do the bias audit stuff?
Yeah, sure. So first, moving to this part, we are going to talk about a tool we built to audit for bias and fairness. But first, just to give a little bit of context, it's really about this, awareness effect, because even as of today, and there has been lots of research in recent years about mitigating biases and fairness in the ML community, in our community, in the community of our audience. And there is no still standard procedure for auditing for bias and fairness in practice. So people are still optimizing in building machine learning systems, data science systems, looking only to global performance. So it's here. It's really about this old cliche of Lord Kelvin: if you don't measure, you can't improve it. So we believe that there was a lack for easy to use packages for auditing for bias and fairness. And if we unfold this dimension of bias and fairness, we create this awareness effect. So people can now, they don't have excuse to not optimize for these metrics. And we can benefit on model selection, see if our mitigation strategies actually work, and so on. So maybe, right, you can move to the next slide. Yeah. So this tool is Equitas. but the first release was in 2018. By then, the landscape was really scarce. There were not so many open source libraries in this domain. Fortunately, today there is more offer, and there is IBM, there is Microsoft, there is Google, What If tools and visualizations. There is more and more tools around there, but we still believe that our main goal of making audit and perception seamless integrated in workflow still holds. And Akitas is really so easy to use, and it's really about getting the metrics out there so we can make informed decisions. So maybe you can move to them. Yep. To the next slide. So it's as easy as getting predictions for your instance, the attributes that define your demographics of interest. It can be race, sex, age, or other attribute that makes sense. So once you have these discussions with stakeholders and define what groups do you care about, you should include those attributes in your audits. And it relies on labels. So as we've seen in the fairness tree, most of the metrics are based on the outcomes and labels are necessary to calculate the error metrics that we get on the bottom layer of the fairness tree. So predictions, attributes, and labels, as simple as that. Maybe we can move on.
Yep. One thing to kind of point out is so one of the questions that discussions going on in the chat is about, some of these things that we're using, we're talking about are kind of US specific, right? Race and credit scores. And that's sort of, those are some of the examples we're giving, but every context, every problem, every country, every, culture, you're gonna have these groups that you wanna have as protected groups. Sometimes gonna be race, sometimes gonna be socioeconomic status. Actually, pretty much every time it's gonna be socioeconomic status, right? It's not just race. It's often it's going to be some sex, right? Again, most countries in the world are pretty sexist, but you're going to have to think about, for your problem, what are the groups that you want fairness on? Whether what are the attributes? And somebody's asking, like, can I use an attribution model is not trained on? Exactly. That's kind of the point. Is regardless of what you train your model on, this is not about model training. This is about, you built the model, who does it impact now? And that's where you can bring in additional attributes, even if it's just for auditing, you should be able to bring them in.
Yes, so as I said before, the key principle is simplicity to audit. So the workflow is very simple. So we get our predicted scores and labels. Usually we do this on a holed out test set because we want to have a most accurate as possible estimate of the biases in the systems in holed out data. And scores, labels, the attributes, we pick a metric. Actually, by default, if you don't pick a metric, Akitas will give you all of them, a bunch of them, mostly what Kit showed about the confusion metrics. All of the metrics were there. Akitas is providing. It's not providing you C nor F1 score. I'm sorry about that. And at the end, it really gets out this bias report, which can be at different levels of information. It can be really low level up to confusion matrix by groups, really breakdowns on predicted positives, true positives, false positives, and so on per group. But you can also have error metrics per group, or you can have disparities, or even the concept, if we pass the disparities we tolerate, you can even say which groups actually fail or pass the test.
Yeah.
So if you haven't, yeah, sure.
Well, one thing, to Pedro's point of, if you don't, all of us hate bad defaults, right? So if you don't pick one, we want you to think about it. This is something, it's not automated. So if you don't pick one, it's going to give you all the metrics, which means it's going to force you to think about what are the metrics you care about here, have that conversation. And that's kind of what we want the default to be, is the default is think about it. Don't just automate it because it exists.
which is also a very strong reason why you should use Equitas. So feel free to go to our GitHub page. If you move to the next slide, right?
Yep.
So, actually, before that, when should you use Equitas? Or we have seen the data science pipeline, all the steps, and this is kind of our understanding that are three different parts of the machine learning pipeline steps that in which you should audit. And it's basically post-modeling, right? You have your models, you have your predictions on the test set, you have your evaluation metrics, and now it's time for you to have a look to your bias metrics. So when you're evaluating and selecting models, don't look just for global performance. Take into account these bias dimensions, the metrics that make sense in your specific application. And this is mostly thinking about the personas of the data scientists. So I believe most of our audience today, we probably, we will use Akitas mostly when evaluating and selecting models, but Akitas is not just for data scientists, it's really also for our stakeholders. So if we think about policy problems, which was the context in which Akitas was developed, we think about the policymaker or our partners working on specific organizations, when they get a model that was developed by a third party, it can be a consulting company, it can be a university research group, when they get a model, these personas should also audit before accepting the models and make that last decision and conversation with community, with all stakeholders involved, if it makes sense, if the model is ready to deploy. And actually, this is kind of individual conversations in the sense that unfortunately today we don't have regulation nor external bodies that force this. So each one of the stakeholders involved need to go for this. So before deploying, but also maintaining. So it's not just because you guarantee that you reach your fairness metrics criteria on the test set that you're good to go and you deploy the systems and you don't look for. As we've seen, there are lots of sources of biases, and bias can cripple in anytime. These systems often run forever. Sometimes we even have automatic retraining of the systems. So it's really important to continue monitoring the bias and fairness continuously. Okay, so we can now move on to the part in which I explain how we can use the tool. So we have three different options. The web audit tool is really thought about non-technical people. So as I said, in the case of policymaker or a client, if you think so, if you think about it, they just with a few clicks they can get the report. The Python library, I think it's probably the most the better option for you, for the audience today, is just go with the library. As you have scikit-learn, you get your predictions, not the prediction actually. If you have predictions, predict proba, and you use it to assess your evaluation metrics. You just run an Akitas, as we are going to show in our collab notebooks. And if you really want to automate, you have thousands of models that you train, you are evaluating thousands of models, and you also want to run Akitas in a kind of a batch, you can just use command line tool that will query a database and will output results in a table. So you can even specify a tailored query, a SQL query to get your predictions. So now we are going to skipping. Oh, by the way, this is, if you go to our GitHub page on Equitas, we have a demo notebook on the Compass data.
Yeah, so we're not going to cover this, but this is, you can take a look. It's a very detailed notebook that goes through lots of stuff, but okay. So Kit, can you post that link again for people on the chat? And so instead of going into breakout rooms, because we're going to lose 40 people if we go into breakout rooms, we're going to stay here for this one at least. And if everybody can open the notebook that Kit just posted.
Yeah, and I really want to stress out, if you don't know Collab is very easy to use, and you don't need to care about any requirements, please just click and try it out. It will work out of the box, hopefully.
Gmail.
Yeah, you need a Google account. Sorry, I didn't mention that. We are biased.
Pedro, do you want to share your screen or do you want me to share
Yeah.
my screen? Okay, go ahead.
I can share my screen, sure.
Okay, I will stop sharing then.
Just a second. Sorry about that. So I will reload this. By the way, just to remind you, here on the web page of the tutorial, when you go to the interactive notebooks, you have the Collab notebook link. So just clicking on that. So first thing to do is to import packages we need and Collab, at least until now, they don't support Akitas and you need to pip install Akitas.
And feel free to, either ping in the chat or maybe we'll do some react with the thumbs up or whatever. Just to let us know if everyone's been able to get in and do the pip installs here on Colab. And then, the notebooks here will kind of take you through an example, but, they're also published out there, the GitHub's out there, so you can steal any of this code and modify it for your own uses as well.
It's worth going, Pedro, if you want to quickly just take people through the structure.
Yes, but even before that, maybe, Keith, you can tell a few words about the case study we are using here.
Oh, yeah, do you want to go back to the slide? Sorry.
Yeah.
Maybe we should have. Yeah, so just to kind of set the ground a little bit, we're looking at a program, it's a nonprofit called Donors Choose that was founded, I think, early 2000s, and is, really kind of exists to try to help teachers sort of fill funding gaps, and especially kind of at disadvantaged schools where they might not have the resources, at least in the United States. There's a lot of cases where teachers are paying out of pocket for a lot of resources and things to do things in their classrooms. Organizations, donorschoose.com, you can find it out there. It's pretty large. They facilitated almost $1 billion of funding, affecting 40 million students, though it is US-centric. But about 1/3 of the projects that are posted fail to meet their funding goal. And it's kind of, you meet it or you don't get funded crowdsource crowdfunding platform. So, we set up a quick case study. They published a bunch of data openly. So this is data that you can go out and grab yourself and work with. A KDD Cup in 2014. I think there's actually an update that's out there on Kaggle as well with some more recent data. We're just looking at the 2014 data here. So the goal is, right, well, we want to decrease the fraction of projects that go unfunded. And they provided a bunch of data about the projects themselves, what resources they're asking for, is it technology, books, et cetera. The description of the project, which is free text. The ask amount, how much is it going to cost, how many students will be affected, some information about the teacher, as well as the school and the class, poverty levels, sizes, things like that. And then, of course, the donations themselves, how they're coming in over time. So, we're sort of formulating this as, well, let's imagine that they are going to, create a new program to have some experts come in, review projects that have been posted, and offer some advice and suggestions. Oh, you should talk about it this way. You should add a picture, things like that, maybe. So that's, pretty high touch, intensive intervention. So they, really can only help 1,000 projects every 2 months with this. And it's kind of a made up situation, but very similar to a lot of the sorts of projects that we encounter in terms of resource constraints and size and things like that. So that's a real kind of basic idea. And then where we're picking up here, right, is imagine that we've taken this data, built hundreds, thousands of models, and done some model selection, and now we want to look at the model that performs well. So Pedro, I'll let you jump in.
Yeah, sure, exactly. So as Kit just said, we already train, in this particular case, 400 different models using, just a question, sorry, I'm probably, yeah. Let me just sec. Yeah, sorry, 400 models, and we have this data frame already prepared, which contains the predictions of the model with highest precision at top 1000. So recapping, why top 1000 and not 0.5? Because as Kit just said, there is only resources available to allocate to help 1,000 projects every 2 months. So the test set is for 2 months period, and we are evaluating our precision at top 1,000 for all the projects we are ranking, at the risk of not getting funded on the period they are open on the website. So as you can see, over this 400, over this model, which is the one with the best precision, across all the models, we are picking the one with 0.55 precision. And now we want to inspect the biases of these models. So of this model. So let's have a look. So here we already, maybe, yeah, I thought someone was about to talk. So we already prepared this data frame, which contains a binary scores for the top 1,000. And so it will be ones for the top 1,000 based on the model predictions, and zeros for the remaining projects. We have the actual label, which is a 1 if the project got underfunded. So we want to help these projects. We have the poverty level of the school, of the students. And we have metro type and teacher sex. So here is about, it's not really about the students, it's about, because it's a teacher that applies in the platform for donation, we just also want to check if there is any biases towards the applicant, so the teacher, and how that can affect the students down the road.
I think one thing just to reiterate, right, is that Pedro mentioned is we're not trying to audit the scores of a model. We're trying to audit the recommendations by the model, right? So the model is being used. The model first ranks every project as the risk of not getting funded. And then it recommends the top 1,000 as the ones to help. So that's where the prediction, the risk scores are getting converted into a 1-0 label, exactly. And one is, we're saying we're going to act on these. We're going to intervene on the top 1,000 predicted highest risk projects. So that's the action we're taking. And so we're going to audit the action and not the actual scores, because it doesn't matter if the scores were all shifted by 0.1 down or up, it wouldn't have made any difference to the actions that are being taken. So that's just something to keep in mind is we're converting. And we're not thresholding based on 0.5 or 0.2 or 0.3. We're thresholding based on, we're going to act on the top 1,000 predictions. And that can change if Donors Choose gets more resources. If they get enough to help 2,000 people or 500 people, that is going to change the results of the audit, which is important.
Yes, and you see, in real life, there we don't deploy models based on 0.5. Here also, we start to define what are our reference groups, and we are using the groups that we believe that they might be historically favored or more likely to be favored in terms of getting funded. So, or if it's better if we think this way, but the people that actually need more need what is probably highest is highest poverty, not lower. So we are going to use as reference the lower group. Maybe, Ray, do you want to elaborate a little bit on why we pick these groups as reference?
Sure. I mean, I think so. What we need is first step was, we need to figure out what groups we care about, we want to audit for, and that sometimes comes from regulation, and sometimes it comes from again policy and social goals. But within each, the reference group is important but not critical. You can always change that. It doesn't change. It's sort of, so in this case, we want to make sure that the groups we think might be privileged, we want to start with that. But there are a few presets, right? So we have an option for taking the majority group. Whichever one is majority gets taken as reference. So we calculate disparities against that. We can do it based on the one that is that has the lowest error rate. And so right now we've customized, we just put in, richer areas as a reference group because we think they might be privileged. Again, this data is from the US. So generally in the US, urban schools are underfunded compared to suburban schools. And so we've put in the privileged, what we think is privileged suburban rural as the location of the school. And then we want to make sure that the students are not disadvantaged based on if they have a male or a female teacher, right? Which students get help should be independent of the sex of the teacher they have. And so we've put in, traditionally males have been advantaged in these type of things. We've put in male, but we'll see later what the error rates are on each of these groups to adjust. So
and
that's, the question here was, can we do multivariate? Not right now trivially, but you can sort of create a new attribute. So if you just create a new, that was just a concatenation of, let's say, teacher, sex, and poverty level, and then use that to audit. Because somebody else asked before, can you audit for attributes that were not in the original model? Well, yeah, you just have to have a column for it. So if you created a new attribute that's the concatenation of the two, then then you can audit by that.
And as just a reminder of the fairness tree, in this case, we are looking for recall parity because we are intervening only, as Kit mentioned before, on a small fraction of the projects that get underfunded. So we pick as metrics TPR, our disparity tolerance. This is more for a visual guidance. This is somehow arbitrary. Literature sometimes uses 80%, which corresponds to 1.25. So we are putting 130. It's just for us to give a clue if the groups are close or not in terms of our TPR, of the TPR. And you see, this is just running the default standard Aikitas audit. It's just as simple as initializing group metrics and bias metrics. We call the get cross tabs, which is actually the centerpiece of Aikitas. It's just breaking down the confusion matrix for each group that we define. And it does so for all the attributes we pass as the attributes we care about. It will break down for all the values of those groups. It must be categorical columns, and we'll break down the results for all of the groups. As Ray mentioned, we are now using the disparity as predefined for the reference groups that we define above. But there are two other ways of doing it. We can use mean metric, we can use the majority groups, and we pass the output of the get cross tabs, and we pass the reference groups dictionary in the original data frame, because Akitas never removes information. It's keep adding columns to the result. And also we need the original data frame to do some other calculations. And maybe we can now show our new plots, our new visualization of Akitas, which is very easy and intuitive. And as you can see, we have on this side, we have disparities, so ratios between groups. And here we have metrics. And our metric of interest is TPR. And on the column metrics, we are showing the actual absolute value of TPR between 0 and 1, while on the disparity side, we are comparing different groups with the reference group. So as you can see, the lower poverty level was defined as reference group, and then we have the highest one, and as you can see, the highest has almost 3 times smaller recall than the reference group. So from the projects from schools in which the students have highest poverty levels, the model with highest precision at our global performance metric is basically privileging the lower poverty level schools. So it's missing 3 times more the students actually need, the project actually need funding. Also, we can see that the group size of highest accounts for 56% of the test set, while the reference group is 43%. Now we can have a look to the metro type.
Pedro, just real quick, somebody was asking in the chat about the difference between the disparities graph and the metrics graph.
Yes, so the metrics graph is really showing the actual breakdown TPR for each group. So group-wise TPR. So the group-wise TPR for highest is 0.05, while for lower is 0.14. And the disparity is actually showing the ratio between the highest with the TPR of the lower. So it's basically the ratio of 0.05 and 14, which means that it's 3 times smaller the TPR for highest than is for reference. So this is really showing the ratio. So we usually look at 2 things. We look to the disparities and we also look to the metrics. We want to see if the project is, if the model is doing well or not in the group-wise metrics, but also the disparities, because it might be doing well for really poorly for the metrics, but the disparities are equal, but it's really poorly on the TPR. And so it's very important to look at both at the same time, both the disparities and the actual values of the metrics. More questions?
And this is where the one thing, actually, yeah, keep going. It'll show up in the third one.
For the meta type, we see similar behavior in the sense that, as Vaida was mentioning, urban schools are more at risk, and actually the model is biased against schools from urban areas in the sense that the recall for those groups is 3 times smaller than the recall for suburban and rural, which is a reference. And for the teacher sex, now we have an inversion here. So the reference group is male, but actually the reference group is not being privileged. The group that is being privileged is female. So teachers, female teachers are more successful at getting predicted positives by this model. And Raid, you were saying something?
Yes, that's the thing I was going to say. Is, in the beginning, we sort of picked. So just by the way, some people asking different components of this graph, right? So the gray dot is the reference group. The other colored dots are the other groups. The two vertical lines are the tolerance that we set up.
Yes, sorry, I forgot to
And then
introduce
the radius is the size of the group, right? So sometimes you might have a group that's 3 people, in which case, depending on the goals of the project, it may be important to make sure you're fair, or it may be an error in the data. And so you want to see that pretty quickly. But this is important, is that we arbitrarily pick the reference group in the beginning based on sort of our intuition that, oh, males are going to be privileged, have a higher rate of some sort. And here we find that it's the opposite. So it doesn't mean that once you've picked it, you can't correct it. You can still go back and do this. But what this is showing is that there is a disparity, right? That projects submitted, we have a higher recall or higher TPR based on our model for projects that are submitted by females than by males. And this disparity, we have to decide what we want to do about it, right? So in some cases, the disparity would be lower rate, some cases would be higher rate, and then it's the next question of what do we care about doing?
Yes, and also we can have a kind of a low-level vision of the disparities across all the metrics, as you mentioned before. So you can see that the TPR disparities, so highest divided by lower as a disparity of 0.36, which corresponds to 2.7 times less. So the TPR for highest is 2.72 times smaller than the TPR for the reference, which is lower. And also we can go even one level down. So the actual TPR and the actual absolute numbers for each group. Number of predicted positives, predicted negatives, false positives, false negatives, true positives. How many of the group have level positives? How many of the group have level negatives? What is the group size? And this is really the lowest level, really the confusion matrix by each attribute name and by each group within the attribute. Just keep in mind that recall is calculated, the metrics are calculated within the attributes. So the disparities are across the groups for poverty level and for metro type and for teacher sex independently, the disparities. Any questions on the single model audit?
Yeah, there's a question on there's a question on sort of when you do the audit is based on historical data, right? So absolutely, I think when we do real projects, you have these audits in the historical data, but then you want to do actual experiments, randomized trials, A/B testing, to actually test even the effect of the interventions, but also trying to see what the biases are in the outcomes, right? So that's exactly how you would do this. So once you've run that experiment, you would then again use this type of audit tool to then measure measure the biases and the outcomes, right? As we were saying, if you think about this, these are audits for any decision-making process, whether it's human, whether it's machine learning, it doesn't really.
Exactly. Even in a project with RAID, we actually audit human doctors and the decision-making process on diabetes screening. We even were able to audit the current practice of the experts, as RAID mentioned in the beginning. So compared to what? You can also compare to that previous or current practice, either if it is based on humans or hybrid humans and machines, or just the model predictions. And it's also very important to keep in mind that if you want to audit a system that is in production for the last month and you have the labels, you can just audit, and it's not historical data. It's data that is actually being used in production. Right, shall I move to the other one? Okay.
Yep.
So we go back to our.
So the things, by the way, you can change here are, you can add all the, we picked one metric. If we had left the metrics out, it would run all of them. You can pick multiple metrics. You can change the tolerance. You can change the reference groups. And then you can go deeper and deeper. So right now we kind of started with, a lot of this was sort of started with, for policymakers looking at overall, you just spent a lot of time. So what happens is often, like, take the compass type example where somebody gives you a model that they've built and you're going to start using it. But before you use it, you should audit it. And if it fails, then you should decide what to do about it. So that's the first output we showed here. But underneath it is all the different metrics and actual predictions. And so we can keep going lower and lower and lower. It's all stored underneath in the tool, in the database. So the longer notebook that we have that was linked from the slides goes through there's a lot of documentation on going deeper and deeper into each of these things.
Yes, so maybe we can move to the bias reduction one. Actually, I might need to think I lost the. Once again, because this is Colab, we need to install the dependencies.
Did you plug in the link in the?
Yeah, I can do that. I can find the.
So just to kind of set the stage here, oh, that didn't get changed.
Oh, yes.
So here's the link to the notebook that Pedro just opened up. Now, if you want to work along as well, if you go back to the slides and kind of given the time, we really want to focus on the notebook and the hands-on piece. We kind of talked through, right, and a lot of the questions in the chat actually were, well, what's next? Great, we did this audit. What do we do now? And what's this kind of iterative process of it? And so, here we're going to talk through and work through a couple of bias mitigation options and strategies that are out there. And broadly, you could kind of conceptualize these as sort of pre-processing, right? Can you do things with the data itself upstream of the model in processing, which is where a lot of, I think, ML work kind of takes place, right? Regularization, constraint optimization, things like that. Can we sort of fix the model itself? And then post-processing, can we adjust the scores or thresholds to sort of debias, even if the model itself is kind of treated as a black box. And so this next notebook is going to kind of take us through a couple of those different options, as well as kind of even upstream of that, model selection, right? We selected a model for this audit based on precision alone, looking at the performance on the precision at the top 1,000, grab that without thinking about bias, and then audited it for fairness. But here we can do that sort of audit for all the models that we build, and kind of think, conceptualize model selection on 2 dimensions, not just one, and think about that. So that's where this notebook will kind of take us through. In the slides, there's a bit more details about some of the papers that are out there and kind of conceptualizations. But I think in the interest of time, really want to focus on the more hands-on component.
Yeah, exactly. And as Wade mentioned before, in the slides, we have lots of things we are not covering here because of time, but we also have an overview of these different or some of the most popular approach for these different types of methods.
Okay.
So yeah, just need to go
And again, our initial idea was to break up into three breakout rooms, and there are three. We've kind of implemented three strategies here. One, well, we'll start off by looking at, we pick the best model, best as in, the arbitrary metric of precision at 1,000, ignoring any fairness. Could we have picked, we have built many other hundreds of models. Could we have picked a different model that would have been fairer without doing any extra work, just model selection phase? And that's one of the questions there. Then we'll pick one resampling technique, right? So how can we fix the data a little bit to make models fair? Can we regularize? And so we pick a technique from in post fixing. We pick one from each. There are many others in each of these buckets. So one thing, if people are interested in helping afterwards, is to add other techniques into this, so that other people can start using them.
Yes. So as Ray mentioned, we added the model with highest precision. That was actually a random forest classifier. Here are the hyperparameters. We also ran a k-test for all the 400 models, and we already have that pre-calculated in here, but it's basically, as you have a for loop, you run a k-test and you keep concatenated the results of Akitas from as you've seen on the previous notebook. And now we want to plot these two dimensions of both bias, metrics, and performance to kind of have a bigger picture in terms of model selection, where we are and what are the trade-offs involved. So we are doing it for poverty level and for the highest. So we have seen in single model audit that the highest is being disproportionately unfavored in the sense that it has a smaller TPR compared to the lower poverty level. And let's see how it looks in terms of global precision and the disparity in terms of the highest. And actually we are flipping here because it's easier to plot if instead of showing disparities between 0 and 1, we are flipping so we can see it the inverse, so we can see between 1 and beyond. So here is the model that we have audited, and here is the landscape of the other 400 models we have trained. So the question here is, we want to be right here. So we want to maximize global performance, and we want to reduce disparities up to 1. So we could have picked this model, which should have lower precision, but also lower disparity in terms of highest poverty. So now it's really a menu, a nuanced menu of a trade-off between global precision and disparities. And once again, this is really about what are the goals of the project and what are the constraints, and this tension between efficiency and fairness.
Yeah, and I think one thing to look at here is that, yes, this is a menu, but this is not a, like, this is a function of what hyperparameter space and model space you chose to explore. So you could have built 3 models and you wouldn't have these options. You can build 1,000,000 models that are all about the same and you wouldn't have the spread. So this is kind of, doing a bunch of things and hoping that one of them gives you the right answer. So we don't recommend that as a way of doing this work, but given that you've built models, that's the minimum you can do, right? At least look at the 2 dimensions as opposed to looking at just 1 dimension, which is, before we were looking at the x-axis and picking this one. This is adding a y-axis on disparity on the work you've already done. So this is minimal extra work and could be beneficial, but this is not explicitly trying to be unbiased or reducing the bias. It's not the way to do this, but we're just sort of showing you, what if you just did that? What would happen? And it looks like you have tons of options available to you. You could have just gone down, with very little hit in precision, the dot underneath it, you could have reduced disparities quite a bit. And that requires very little work. So that's kind of the idea here.
And just a quick thing, if you're running the notebook, Colab seems to hide a bunch of cells by default if you go up under
Oh,
view, and I
sorry.
think Pedro, you might still need to do this, and hit expand sections.
And I recommend you all.
I'll throughout the notebook and make things.
And let's now have a look to the urban and metro type. So what would be that landscape here? So the model we added is here. And once again, not once again, but just remind you that we are doing that on group by group fashion. So this model here might not be the same that you get over here. And that's also important to keep in mind. And finally, based on the teacher sex. So here we see a kind of a larger spread, wider spread of disparities in these 400 models that we arbitrarily picked and we randomly sampled to create this network. So maybe now it's time to, what if we apply bias reduction strategies? As we mentioned before, and as you can find in our slides, sampling, regularization, and post-hoc adjustments. And shall we start with resampling rate, or shall we go and jump to a specific mitigation strategy?
Let's start with resampling. It's fine. And we can quickly. So there are three of them here. We've got the resampling one in the menu on the left. Will you can move back and forth. They're all independent, and you can compare them as well. Yeah, we can start with resampling.
Okay, so now we need to have the training data frame because we are resampling on the training set. So what if we not use the full training set, but a sample that we create? What would be the performance and bias results of the models we would obtain with that sample? But for this tutorial, we are picking and sticking with the same model configuration that entail IS precision, and we want to see if by resampling we are able to get different bias results, hopefully reduced disparities. And we are here, we're just loading that model. We are creating a classifier. And then here we are defining what is the attribute we are focusing or resampling on. What is the group of interest is highest, and what is the reference group, it's lower. And
yeah, so just as you're doing this, so this is one of those things where we're going to see if it works or not, but in practice it rarely works well, and we'll see if it works here or not. I mean, we know the answer, but the intuition behind this, and people do this empirically, it's sort of one of those things where you're saying, well, if a group is really small, it doesn't have enough representation. So what if I balance my data set? What if I've got poverty level as high and low, and poverty level high is only 5% of the data? What if I balance it, and I do 50% low and 50% high? Will that help? And maybe. The other thing people do is say, well, the prevalence of poverty level high is only 3% positive labels in there, whereas poverty level low has 50% positive labels. So maybe I change the prevalence, and maybe that's going to make the model more fair, and I retrain, or maybe I do both. So you can try those things. They're kind of more ad hoc, empirical, and in a lot of, just fair warning, a lot of projects we've tried it on, it actually doesn't work. We wanted to put it there because it's a commonly used approach, so that you can try it and see if it works for your project. So we're not endorsing any of these things. We're just putting them out as there are 3 common ways people do this, and we're giving you a place to sort of try them out.
Exactly, and also our Akitas can help you to see the differences between using one strategy and another. And as already was mentioned, we could just equalize group levels, or we can just try to equalize the prevalence. Ideally, you do that for all the 400 model configurations you sample, and you do all the resampling, and you retrain all the models, and you compare. Here, we are just focusing on that blue model we picked before with the highest precision. And so let's just recapping. Our attribute is poverty level, group of interest highest, and reference lower. So here, we are basically defining the number of instances or the sample size for 4 different subgroups. So for the group of interest, which is highest, how many samples we want positive, how many we want negative, and for the reference group, which is lower, how many samples for label positives and for label negatives, and that would change the prevalence. So we are trying to equalize the prevalence on the training set. So before we had 6,000 label negatives on the group of interest on the, maybe someone on the background noise. Yes, we had 6,000 label negatives. And now in order to equalize the prevalence, so we want to shift the prevalence of the lowest, of the highest group a little bit up, because it was 33-ish before. We are just picking 5,000 of label negatives. And here we are basically picking all of them. And now let's sample. And we create a sample. We are not fixing the random seeds, so this is picking different samples every time. And we just train the same classifier now with the new training sample we created. So basically we are concatenating all these samples we created in a single training data frame, and we are fitting the random forest, and now we are going to predict. And actually in this sample, we got a precision of 0.571. If we resample again, we might get a different number or the same number. Yeah, similar-ish.
Hey guys, I'm so excited to tell you that I'm working on a music video for Levitating, and I want you to be a part of it. Whether it's choreography, makeup, animation, it starts.
Thanks, Pranjal.
So let's see how it was before, right? I just pasted a bunch of things here, sorry. So before, once again, recapping, we had 3 times disparity. So 3 times smaller TPR for highest poverty compared to lower. Let's see now for the new model what we get. And apparently on this test set, we increased the TPR of the highest group, and we reduced the TPR of the lower poverty level group. And once again, we are not endorsing these approaches. We're just trying out on an old out test set.
Yeah, I mean, I think our suggestion would be, you know, we're not saying, oh, this one's always going to work. This way, you know, it's kind of your mileage is going to vary, really depending on the context and the features of your problem. And I think, you know, often our approach is more empirical in the sense of try, you know, kind of saying, well, try a lot of things and, you know, and kind of investigate different options because you don't know how this frontier might move.
Yeah, like this is a surprising result for this problem, at least, right? Where you got the disparity went down for this, for TPR, for this attribute, and the performance didn't suffer. It actually increased a little bit, which is some noise and other things going on that we're going to ignore for now. But that's not a result that we've seen very often, to be honest. So that's why it's worth having an option there to kind of check it out.
So maybe it's time now to move to a second strategy. So this time we decided to try one of the toolkits out there focusing on mitigating bias. And Microsoft just released recently this FairLearn library. And the main method they implement is a reductions approach. You can see on the slides, this is a paper from 2018. So basically the idea is to use constraint optimization in the Lagrangian to account for not just the loss, but also the equalizing true positive rates across the groups. So here, we are defining that our constraint on the optimization problem is true positive rate difference. So we want to minimize this true positive rate difference. Our Bayes estimator, and this actually works with any Bayes estimator that exposes a fit and a predict. It can be LightGBM, it can be logistic regression, and so on. And it's now trying to create a bunch of cost-sensitive estimators. And this one, because this constraint optimization takes a little bit longer. And the dataset is quite small. Also, there is, as I mentioned, because we can change the Bayes estimator, we can change all of these hyperparameters. Here we are just showcasing almost kind of default settings. You could try many of them, although as I mentioned, it kind of might be a little bit longer to do so if you have a large data set. But now, as this is a constraint optimization problem and there is no notion of thresholding or scoring, it's trying to optimize for the 0.5 decision boundary. So what actually ends up happening is that to fulfill our constraint, which is equalizing to positive rates, the method just exposes a dot predict and ends up predicting as positive, not the 1000 that is actually the real life setting and constraint, real life constraint on our case study. And it really increases the number of predicted positives to equalize the true positive rate. So how can we audit this? Well, we can still think of in real life, we would sample instances from this top 6,000, we would sample 1,000. So basically, if we audit these predictions, we would get our average bias results. So let's compare again with the previous one. And now let's look to the new one. So it seems it also reduced the disparities. So now the highest poverty is a TPR of 0.41, because once again, this is a byproduct of increasing the number of true positives by 6 times. And now the TPR for the reference is 0.5. You know, almost we wonder if for other thing, if we should keep with the TPR, but in real life we'd use the TPR, so we are just comparing the disparities here, which as the number increases, the disparity might tend to get closer as well. So the previous one is a 0.55 precision. What about the new one? Well, actually, it increases a lot the number of predicted positives, but because our performance metric is precision, as you'd expect, as you increase the number of predicted positives, your precision would go down. And in fact, here we would have a 0.40 precision. So let's see how it would look like in our bigger picture of multi-models. Well, actually, this is a result of the regularization. Maybe Keith and Ray, do you want to comment?
No, I think it's kind of obvious. No comment. It doesn't work here. Yeah. The only thing to think about, I guess the comment to make is reiterate what Pedro said about a lot of these types of tools are a little, are not customizable, right? So here we would want something that does this optimization for maximizing precision at the top 1,000. Because a lot of these tools are not designed for that, in practice, it's giving us 6,000 positives. Now, Donors Choose or any other organization using it doesn't have resources to help 6,000 projects. So they're gonna have to pick 1,000. If the prediction is 1 and 0, then all ones are equal. So up to 6,000, they'll pick 1,000 randomly. And a lot of this reduction in, what's happening is that that's the cause of that. But that cause is in practice hard to fix. If you use this method off the shelf, then this is the best you can do without tweaking it and trying to change the regularization to optimize for precision at top 1,000. And that's something we have to kind of consider when looking at practical trade-offs for these types of tools.
And even if it was giving us a score where we could, a running score at the output where we could threshold the top 1,000, because the constraint was around the, the kind of default, right, 6,500 or the 0.5 threshold, thresholding it at 1,000 would probably kind of throw away that fairness constraint, and we see that with other methods out there. So yeah, I guess maybe this is also a little bit of a call to the research community of like, we need more flexible methods and options for doing projects as they kind of occur in the real world, which is often not with a kind of default boundary or 0.5 score threshold.
Absolutely.
Okay, so let's try to kind of get through this in 5 minutes and then.
Okay.
Yeah.
So another family of approaches is post-processing or post-hoc disparity mitigation. So you train your classifier, you get your predictions, and now you might want to define different thresholds for each subgroup. Here we are showing an approach for equalizing recall, because once again, this is our metric of interest. So this would imply that we would get group-specific thresholds in order to equalize the recall across groups. So once again, we are not retraining a model, we are at the model, we have the predictions. It's just defining specific thresholds for specific groups, if that is possible in the scenario. So we are training again, and this is happening because this is a long notebook and it's on Colab, so we need to rerun things again. So here we are sorting our predictions by the score, and now we are breaking the data frame that is sorted by prediction for each subgroup. So each subgroup will have a data frame with the scores sorted. And for each of the groups, what we are doing here is we are getting the sum recall. So as we go down this sorted list by predicted score of the model, as we go down, what is the recall at that instance? And that's as simple as just the sum of the label column as we go down the list sorted by scores divided by the total number of label positives of the data frame. And now we are concatenating these two data frames. So one data frame is the sum recall for one group, the other one is the sum recall for the other group. We merge it. And now we can have a look how is, if we pick the top 1,000, how is the tail of the top 1,000 look like in terms of sum recall? And here we are seeing like the lowest predicted positive on highest as 0.13 recall, and the lowest predicted positive on poverty level lower as 0.13 as well. And I forgot to mention, but because now what we are doing is getting the numbers of instances per each group that should be considered positive, this is a new parameter that we are learning, let's say, or defining. So what we have done so far here is on a previous split in time that we use in order to not overfit on our current test set for these parameters. So now we go back to our split, train test split and our current test set. And now we know these two parameters. And let's just very quickly get the new predicted provas. We sorted by predicted prova, and we use the case that we learn for each one that we know that each group should get. Sorry. Once again, we are going the audits, and now we can see that we went from, again, from almost 3 times disparity to below 1 disparity here. So it's very close. And what about the precision? Well, before we had 0.55, now we have 0.58. Let's see.
And by the way, this before and after is not, you know, the way it sort of, the data is changing. So the training is on the past and test is on the future. It's the same test set, but it's changing.
Exactly. The before here means the non-mitigated model.
And
so any comments here on maybe Keith and Wright?
Just a quick thing here, right? So I think we're finding in the chat, there's a conversation going on about, you know, somebody's asking about cost of fairness. And here we're seeing that at least on the trade-off, there is no cost. There's a cost in doing this work, right? The process, like we have to do extra work to get fairness, and that's the cost here. But there is no trade-off cost here. We're seeing that we can get a fair model or without sacrificing precision or efficiency in this case. If we allocate resources to 1,000 projects before and after, you're about the same number of deserving projects or, you know, at-risk projects across poverty levels get funded. So we haven't lost efficiency and we've gained fairness. So there isn't always a trade-off. And we find this repeatedly in many projects. This is not an outlier problem. We find it fairly regularly.
Any questions about notebook on the chat? I hope everyone is running it. So maybe it's time to wrap up.
Yep.
Oh, I see it has been an active discussion. I'm missing 84 messages on the chat. Well, I'm just talking. It seems everyone is on the chat and I'm here just talking.
No, that's the good thing about multiple presenters is, you know, a couple of us can take the chat and move. Yeah, so let's see. Yeah, so I think, you know, this was the breakout room not working very well. We thought we'd just stick it to a single breakout room, and hopefully the notebooks exist for everyone to play around with, modify. A lot of the stuff, you know, we've tried to kind of give a structure to, you build models, a bunch of them, you then pick, if you're unaware of fairness, you just sort of pick the best one, you audit it, you find there are problems, and that's pretty much always going to be the case. Every project we've worked on, if we just blindly pick the best model, we find it's biased in lots of ways. The first step is, you know, we step back and look at, well, all the models we built, are they all biased? Is there a trade-off? Is there not a trade-off? And then we go deeper and say, okay, let's try to fix this. And so we try an approach, we audit that approach, and we compare it to what we were initially. And we try a different approach, we audit, and then we compare them all, right? So if we actually go back to the slides, wait, where were we? For the regroup, we find, you know, this was sort of, for poverty level, this is what happened. Our original best model was here. And for now, take these additions as noise, right? The improvements, it's random, but we could, resampling seemed to work here, right? It kind of got us to parity without reduction in precision. We find in practice, that doesn't happen too often. So it happened here, and we wanted to sort of show it. The regularization approach that we showed here with the FairLearn didn't really work. It got parity but hurt performance. And then this post hoc correction worked, you know, similarly. And so what we've actually find repeatedly is that this post hoc correction stuff by far works much better than a lot of other things for these types of problems, where we're looking at TPR and recall, limited resources, assistive interventions. And so there's some papers here that talk about some of these things. So, and we have sort of, you know, some of same, if we had done this for metro type, urban versus rural and suburban, we would have gotten very similar results. If we had done it for teacher sex, there was a little bit more variation here. This is what we got, right? So the post hoc one did much better in this case. So you can sort of try changing that and doing different things. But again, overall, you know, we've kind of focused a little bit today because the short of the time in the overall model. But we want to sort of make sure that you also look at the actions that you're taking. And so the big sort of question really is here, the thing to remember is that fairness and equity and bias is not a thing that you do just at the modeling stage, right? It has to be kind of entire part of the project. When you scope a project, and we have lots of resources for scoping projects, by the way, that are data science and where you kind of think about these goals. How do you include the community in these types of conversations, or what does it mean to be fair and equitable, and metrics and the validation and monitoring, the A/B testing somebody was talking about, that has to be embedded in the whole process. Understand how each phase of the project could lead to downstream bias. Making sure that, you know, this is obvious, but a lot of times, you know, people forget that, like, oh, I can't get total fairness, so I should not do this. Well, every metric is not the same. So think about the fairness tree. Explore reduction strategies. Some of them work, some of them don't work. There's a lot of theory on bias reduction right now. There's very little practice. So a lot of it is, our work has been, we've developed some of these methods, but we're also testing new ones empirically to see what happens. And then, you know, remembering that we have to think about the overall system and the overall actions. And then this is a lot of the questions, some of the questions coming were around company culture and, you know, what if my manager says it's performing really well, why are you worried about bias? I think a lot of it is cultural. Either, you know, in some industries, as the conversation's been going on in the finance world, you know, there are regulations in place. In many industries today, there aren't regulations. And so we have to kind of think about how do we create these environments? How do we embed ethics into these types of things? Thinking about the data pieces, thinking about the people, how it affects people, and then really overall embedding ethics into both the technical tools. Right now, a lot of it is embedded in the human processes, but very little of it is embedded in the technical process, in the machine learning pipeline and audits and model selection and monitoring and A/B testing. Bias is a thing that does not really standardized yet. So part of it is how do we standardize the implementation of these tools, embedding of these tools into pipelines. Any standard machine learning pipeline should have these tools that get run. So that's kind of, you know, what we wanted to talk about. There's a bunch of links around, you know, here. There are other resources that we've left for you guys to look at. This is some project scoping, the tools, some write-ups. So this talks more about the fairness tree and goes deeper into that. It's in free, open, available, a bunch of different things here, some books. This is a new, separate, but we'll plug in. This is a recent, earlier this summer, we launched this, this platform, Solve for Good, that gets volunteers who are interested in working on these types of data science and social impact projects. So governments and nonprofits submit projects, and then we connect them with volunteers, and you can sort of, if you're interested, go check it out, sign up. And yeah, any thoughts, Kit, Pedro, when we wrap up?
No, I mean, you know, mainly just thank you everyone for indulging us, and also the great conversation in the chat and the breakouts and everything. The link, which we posted a couple of times and should be available through the conference and stuff, you know, has all the slides, the code for these notebooks and whatnot, links out to Equitas, the tool, and some more detailed notebooks there. So there are a lot of resources. Obviously, feel free to, you know, grab or, right, like, you know, modify and use any of that, of course, but also, of course, feel free to ping us. Our emails are here. You know, always happy to be thinking about these things as well.
Yeah.
Yeah, and just to complement that, I think many times we are stuck in somehow superficial conversations, and we just showed today that there are tools out there. Of course, we need more tools, but you know, these notebooks are fairly straightforward to use. There is really no excuse for trying these reduction approaches out it when you're developing models. It's really like very easy to use.
Yeah, thank you, everyone. And we posted in the chat, you know, feel free to ping us if you're interested in having more discussions or working on any of these things or helping us extend. One of the things we want to do is put these type of tutorials out there so other people can also teach them. So if you're interested in, you know, working with us on expanding and delivering these types of tutorials and extending the toolkits or combine, you know, adding more things, let us know. We can always, you know, use the help. So thank you.
Thank you. Bye.
Thank you.